Problem 2.1. This is on page 31. So problems 2.1 to 2.4 revolve around solving differential equations, which is what section 2.1 is all about. So in this problem, we are asked to solve this particular differential equation. And this is a second order linear differential equation. So let's assume the solution is of the form e to the power sx, where we don't know what s is and we need to find it out. So the first derivative would be e to the power sx times s, and the second derivative would be s is a constant, so we're going to take the derivative of the first derivative. So it will be this, so it's going to be s squared times e to the sx. So if we were to plug this value in this equation, we will get s squared times e to the power sx plus s times e to the power sx minus 6 times e to the power sx is equal to 0. Now we can forget e to the power sx here. We can just cancel it out everywhere. And we end up with an equation s squared plus s minus 6 is equal to 0. So it's a quadratic equation. We can solve this equation by writing s as 3s minus 2s and factoring things out. So that implies s can take the values of plus 2 or minus 3. And what does this tell us? This tells us that the solution is of the form e to the power 2x, or it could be of the form e to the power negative 3x. When there are two independent solutions, where one solution is not just a multiple of the other, in this case, these two are two independent solutions, a general solution for the differential equation can be written as a linear combination of the independent solutions. So this will be a solution to this differential equation. Now let's move to part B of the question. Evaluate the arbitrary constants in the solution if the boundary conditions are y equals 0 at x equals 0, and the first derivative is equal to 1 at x equals 0. So the arbitrary constants that we have are C1 and C2. Now we're going to make use of these boundary conditions here to identify what C1 and C2 are. So the simplest way to do this is to, first let's write down our differential equation, the solution to the differential equation, which is this. Now what we're going to do is plug in the values of x equals 0, y equals 0, and the first derivative equals 1. So we have these values here. So what I'm going to do is I'm actually going to plug in these values in the differential equation. So we have the differential equation here. So that would be y, second derivative of y plus first derivative of, second derivative of x plus first derivative of x minus 6 times y of x equals 0. At x equals 0, y of 0, let's see what that will be. Y of 0 will be C1 times e to the power 2 times 0 plus C2 times e to the power negative 3 times 0. And e to the power 0 is 1. So this is going to be C1 plus C2. So that implies y of 0 is nothing but c1 plus c2. However, the boundary condition tells us that at x equals 0, the value of y is equal to 0. So this should be equal to 0. Now this tells us that c1 is nothing but negative of c2. So we have some relation between c1 and c2 here. We still don't know what they are, but if we know c1, we can definitely know what c2 is using this relation. Now let's compute the first derivative of y. The first derivative of y is nothing but, from here we can compute the derivative. It's going to be c1 times 2 times e to the power 2x plus c2 times negative 3 times e to the power negative 3x. Now, let's plug in the value of x is equal to 0. We know that the first derivative is equal to 1. That's the boundary condition, right? So that implies the first derivative at x is equal to 0 is going to be equal to 1, which is equal to 2 times c1 times e to the power 2 times 0 plus, or maybe I can just write it as negative 3 times c2 times e to the power this. So this and this e to the power 0 terms are going to be equal to 1. That implies 2c1 minus 3c2 is equal to 1. However, from here, we know that c1 equals negative c2. So I'm going to plug that information in here to get 2 times negative c2 minus 3c2 equals 1, or this is going to be negative 5c2 equals 1, which means c2 is negative 1 by 5 or negative 0.2. So we know the value of c2, and c1 is nothing but the negative of c2, which means it's going to be 1 over 5 or 0.2. So we have not only solved the equation, but we have also identified the arbitrary constants in the solution. So the general solution can now be written as 0.2 times e to the power 2x minus 0.2 times e to the power minus 3x. So this will be the general solution.